The equation y equals 2e to the 6x minus 5 is a particular solution to the following differential equation. So again, if that word comes up, you might not know how to do it if you haven't done that kind of optional section. But a particular solution just means if I plug this function and its derivatives, so you can see there's derivatives in there, all right, and its derivatives into these equations, the equation's true. So what we would have to do to check this is we have our original function. We have to find our derivative and our second derivative. 6 times 12 is what, 72? All right, so those are our three functions, and we plug them in. So if we plug it into A, we get 12 e to the 6x minus 6 times 2 e to the 6x minus 5 minus 30. So I'm just plugging in those exact functions in. I want to see if this simplifies down to 0. And it looks like everything's going to cancel, and A should be the right answer. All right, just to show for B, if we were to do this with B, 12e to the 6x, 12. You get 24 e to the 6x minus 24 e to the 6x plus 60 plus 5. And again, you can see some stuff cancels, but some stuff doesn't. That's why B is not the right answer. All right, we got lucky. A was the right one. If I plug those values in, I get it. All right, chances are these will give you something that don't make sense either. All right, what is the value of x which the minimum value occurs on the closed interval of 0 to 1? So we only care about 0 to 1. All right, for the minimum value is going to happen when my derivative, all right, so it goes when I go down and then back up. All right, but that means our derivative goes from negative to positive. Also means there's a 0 in the middle. So what I'm going to do is take the derivative of this function, right, using our power rule, and I want to set it equal to 0. All right, just to help me, I'm going to, actually I don't need to do that. I'll add 2, divide by 4, and then I have to cube both sides to get 1/8. So it looks like instantly 1/8 should be the answer, and it ends up being the answer, but there's actually two other things. If you're just looking for the minimum value on an interval, you also have to check the endpoints. If I plug in 0 up here, I'm going to get 0. So 0 goes to 0. If I plug in 1, I'm going to get 3 minus 2 is 1. If I plug in 1/8, get 3. Oops. 3 times 1/8 to the 4/3 minus 2 times 1/8. A little bit more simplifying to do here. 1/2 to the 4th is 1/16 minus 1/4. And 3/16 is 4/16 minus 1/4. So this would end up being a negative number, so it's less than these two, which means it actually is the minimum value. But when you are finding a minimum on an interval, you do have to check those endpoints. All right, so plugging in these is actually guarantees you got the right answer, but this wouldn't be a bad guess just from the fact that that's the one option for the minimum could occur. All right, in this case, W of t represents the depth of the water. All right, and we want to figure out what this inequality is going to mean. The first thing, as soon as you go to a prime, that's to do the rate of change. All right, so W prime represents the rate of change of the depth of the water. All right, so it's not going to be A, because that just says the depth of the water is increasing. Actually, that could be potentially it. So hold up, let's read through these a bit more. All right, so 2 hours after the tank begins filling with water, so that's 2 hours from my time, the depth of the water is increasing at a rate greater than 3 feet per hour. All right, so that might still be it. So let's say over the first 2 hours. Well, this isn't over the first 2 hours. If we're doing something over the first 2 hours, you have to have an interval. All right, 2 hours after the tank's being filled, the rate at which the depth of the water is rising is increasing at a rate of 3 feet per second. and D. All right, so we have to figure out the difference between A and C. And this one says the depth of the water is increasing at a rate greater than 3 feet per hour, or the rate at which the depth of the water is increasing or rising is increasing at a rate of 3 feet per hour. All right, so if the derivative is greater than 3, right, the derivative is the slope of the tangent line. All right, we know it's bigger than 3, so we know the original function looks something like this blue line. So our original function is going upwards at a rate of 3. So the depth of the water is increasing at a rate greater than 3 feet per hour. That one seems like the right one to me. Let's see, C again, the rate at which the depth of the water is rising is increasing at a rate. So if the rate was increasing, that would have to be something with the second derivative, because the rate's already the first derivative. And then for that to be increasing, we need to know something about the second derivative. Since we have nothing about the second derivative, to me, A seems like it should be the right answer. A person turns 30 feet from this point. Right, we want to know what is the rate of change in radians per second of the angle. All right, so first we need to figure out some equation that's going to relate the angle in this picture. All right, well, we know something about this side, and it's 40. All right, so we're thinking about angles and sides of a right triangle. We have tangent, so the tangent of this angle is going to be, this side's not constant, so I'm going to call it x. This side is, so I can keep it as 30. All right, so that's what I know so far. And now I want to start using rate, so I can take the derivative. Take the derivative of tangent, I get secant squared. And this is a, oops, didn't mean to put an equal sign. This is a related rate problem. So whenever I take the derivative, when there's multiple variables involved, whenever you take the derivative, you're going to get a d theta dt. Take the derivative, I can pull out the 1 over 30, and then dx dt. And I'm trying to figure out the rate of change of the angle, so I'm going to isolate that. So I'm going to get d theta dt equals 1 over 30 times dx dt times 1 over secant squared. I'll show you why I did that in a second. But there's some things I know. The x dt, the change of this side, is 2 feet per second, so that's 2. I guess it's rising. If it was coming, the balloon was coming down, it'd be -2. And then 1 over secant squared is the same as cosine squared. And what is cosine in this triangle? Right when there's a 40 here, well, we have a kind of a 3, 4 that has to be 50. And cosine is going to be adjacent 30 over hypotenuse 50 squared. And really now we just have to simplify this. So 1 over 30 times 2 is 1/15. That simplifies to 3 over 5, which is 9 over 25. The 9 and the 15 both have a factor of 3. And we get B. All right, so this is a related rate problem. You set up the equation, kind of do implicit differentiation in a way. You're taking the derivative of things with different variables, and then plugging in what you know. All right, this one's a little bit more complicated because there's extra kind of trick stuff that's thrown in. Right, how many vertical asymptotes does the graph x minus 2 over x to the 4th minus 16 have? Right, vertical asymptotes happen when you try to divide by 0. So in order to figure out when we're going to divide by 0, we need to figure out when this is equal to 0. All right, we can factor this as a difference of perfect squares and do it again on the left one. X squared is always positive, so x plus 4 is negative, never negative. So it looks like these two, all right, the answer should be B for 2. But because we have an x minus 2 on the top, this x minus 2, let me just actually rewrite this equation now. I can rewrite it like this. right, this x minus 2 cancels out. That's never 0, so I don't have to worry about that, and that's going to be one option for a vertical asymptote. All right, and this is the very last problem, and they gave you the craziest question for the last one. All right, for what value of b does this integral equal this? All right, we've seen this symbol just once in class. All right, this little sigma here. And that's a shorthand notation for sum. You're adding a bunch of things together. And the time that we've seen that is during Riemann sums. So we need to figure out, all right, this Riemann sum is equal to this integral for what value of b. All right, there's an x squared here. All right, it's going to correspond to this first part there. So this is the value starting at 1, and you're adding some number to it. So we think about, we have this function. We have all these rectangles. You start at 1 here, and you get some next value, add something to it. Then you have that value, get some next value after it and stuff. So this is basically the notation for getting all of these rectangles. All right. And this is the width of the rectangle because we need a height and a width. All right, the width of the rectangle is 2 over n. All right, n is the number of rectangles you're using, and the width, the total distance, is 2. So you're taking the distance 2 and breaking it up into n different rectangles. All right. And all of that to say is our total distance between these things is 2, which the distance from 1 to 3 is 2, which means B is the right answer. So it's a really complicated way of asking how far are these numbers from 1.